Hi, welcome to module number 41, which covers frames. Recall that we were discussing orthonormal bases, and as before, we have a set of vectors, v1 through vn, and that set of vectors is spanning the vector space capital V. But earlier, we had a situation for orthonormal bases, ON, and that's my parrot pretending to be a woodpecker. For orthonormal bases, n is equal to the dimension of the vector space V. But here, these elements might be linearly dependent. Recall that for an orthonormal basis, the ones that are different, they're orthogonal of one another, hence linearly independent, but now there may be dependencies. And if there are dependencies, n will be larger than the dimensionality of V. Now you may think, hey, I actually want a smaller n. I want it to be equal to the dimensionality of V. I like orthonormal bases. This is not efficient. Possibly so, but it could actually be a good thing that n is larger than the dimensionality of V. And let me explain. What if the coefficients with respect to these n vectors have more explanatory value? So imagine that for an orthonormal basis, you'll have dim of V elements, which is equal to n over 2. And now suppose a frame, we have not yet defined a frame, but bear with me here. Suppose that with a frame, you have n elements. And suppose, what is the sparsity? Let me do this in a different color. Suppose that the sparsity with n over 2 elements will be, let's say, n over 10. Okay, so n over 10 out of n over 2 will be large coefficients. So 20% of them will be large. But now maybe with the frame, you have more coefficients in total, but only n over 20 of them need be large in order for the rest to be small. So what I'm saying, when there is linear dependence, there exists a subspace of possible explanations for the data. And within that subspace, there may exist sparse solutions, sparser than before. And that's why this could be a good thing. So now, having said all that, let's define a frame. A frame is a set of vectors such that for every vector in our vector space capital V, if you take the representation with respect to that vector space, so you take inner products between V and the different VI's, for i's going from 1 to capital N. And if you look at the energy, so the energy is the squared magnitude of all of these inner products. That energy is sandwiched between some constant A multiplied by the energy of the signal in the original representation, and another constant B multiplied by that energy. And A and B are numbers, positive, real numbers, positive and bounded. So our intuition is as follows. If you look at the inner products between V and VI and you arrange them as a vector, that vector, its squared L2 norm, its energy is going to be theta of the energy of the original signal. So that's a frame, and for a tight frame, A is equal to B. So let me provide an example. Suppose that you have two orthonormal bases. One of them will be called VA, the other will be called VB. VB, its elements will be VA1, VA2 up to VAN. This is an orthonormal basis of dimension n. So I'll just write in parentheses that the dimensionality of V is equal to n. And now when we're talking about the second orthonormal basis, VB, its elements are VB1 through VBn. So VA and VB, they're both orthonormal bases. Both of them have n elements. And now each of them is a tight frame with A equals to B equals to 1. Why is that? Because we know that for an orthonormal basis, for all v in our linear space capital V, the summation of the squared magnitude of inner products between V and VBI will be equal to the energy of V. So another way of looking at it is VA are coefficients with respect to the space, the orthonormal basis capital VA, or maybe call them alpha A with respect to VA, alpha B with respect to VB. Alpha A and alpha B are both length and vectors of coefficients. The energy in alpha A is equal to the energy of alpha B, which is equal to the energy of V. Okay, so we have two orthonormal bases. And the A equals B equals 1 is because we have a 1 in front of the energy of V. So now let's concatenate them. VC will be a concatenation of VA and VB. And now let's think to ourselves that alpha A is the set of inner products between V and VAI, spanning all the i's from 1 to n. Alpha B is same thing with the BI's. And alpha C is a concatenation of alpha A and alpha B. And now I'm saying, well, what is the energy of alpha C? Again, alpha C is a vector of length 2n. So it is an R 2n. So the energy of alpha C is equal to the energy of alpha A plus the energy of alpha B. All we did here is concatenate vectors, and when we're calculating energy, we sum the squares. And so we're summing the squares in alpha A and we're summing the squares in alpha B. And this is 2 times the energy in V. And by the way, when I'm saying energy, I square the L2 norm. And if I didn't take the square of the L2 norm, it would be the square root of the energy. Okay, so I hope I've persuaded you that A equals to B equals to 2. We have a tight frame in this new representation, VC, because the coefficients alpha C, their energy will always be 2 times larger than the energy in the original signal V. So that's it for frames, and we'll continue next time.